Hey everybody, this is Larry. This is day 19 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. Oh, excuse me. One more, maybe. Okay, maybe not. Oh, okay. My apologies, friends. This is the exciting part about recording this live. Hope everyone's having a good weekend, and hope everyone has a good week coming up. Yeah, I'm 70 days, 10 weeks away from the marathon. I'm both excited and also so tired. So let's get started today's problem. Today I haven't done my workout yet because it's been raining most of the day. So I hope to go after doing this problem and maybe a bonus problem. The raining is still a little bit rough, it seems like. So yeah. All right, so let's take a look at today's problem 650, 2 keys keyboard. There are only one character A on the screen of your notepad. You can perform one of 2 operations on this notepad for each step. Copy all and paste. Okay, so you have to get A exactly using copy all and paste. Okay, so yeah. So I mean, I feel like this is probably going to be some sort of dynamic programming, and with n is equal to 1000, we can even be a little bit, we could be n square, and it'll probably be okay. But okay, so let's think about, yeah, I mean, I think the 2 ways you can think about it is going from, well, what are the states, right? So I think there are two things we're considering, right? One is obviously the number of characters on the screen, but the second one is the number of characters on the pasteboard, right? On the copyboard, clipboard, whatever it's called. So that's one way to think about it. And from that you could do dynamic programming or at least brute force. I think the 2 strategies I would think about this with this one. We'll see if dynamic programming is fast enough. Like I said, there's going to be 2-dimensional for my initial state. Maybe you could optimize this, but for now that's on my head and it is fast enough, so it'll be good, right? So get min. So we have current number of characters and then clipboard or whatever, right? And current is equal to number of current characters, and clipboard is just number of characters on the clipboard, right? and if current is greater than n, then we return infinity, because that means that we overshot for some reason, just in case. If current is equal to n, then we return 0 because we're done, and we don't care about clipboard. And okay, otherwise we can do 2 moves, right? We can, well, copy the characters on the screen. So that means that so best is equal to infinity, yeah. And then this is copy all operation. So then best is equal to min of best get min. So then the current doesn't change, which we copy all, and the clipboard will be the current, right? And then this is this plus 1, of course, for making one operation. Here maybe we want, so that it doesn't go in an infinite loop, we will make sure that if current is not equal to clipboard, right? And it makes sense as well, because you won't keep, I mean, you can keep copying all, but that's just a little bit silly, right? Otherwise you can paste, and paste, is just equal to min best get min current plus clipboard, and then we still have clipboard plus 1, right? And that should be good. I mean, we'll make it slightly faster by saying that if clipboard is greater than 0 for obvious reasons, because that's where we start anyway. And also maybe with current plus clipboard is less than or equal to n. I know that this gets checked, but it does save us a slight function call. And then otherwise we return best, and hopefully this should be good, right? So we return get min, we start at 1, we start at 0 at the clipboard, and that should be good. Of course we have to memorize, but we'll see if it works with small numbers first. Yeah. Okay, I mean, so this looks already good. Of course we can do 1000 here, but it won't be for correctness, just what? Huh. I thought we would have to memorize. Why does this... I mean, in some way, it makes an... I don't know why. I mean, I'm actually surprised here. Oh, I guess so, yeah. I guess so. I guess that makes sense. Because I'm trying to think about the worst case without memorization. I thought we would have to memorize. I'm going to submit this just to... because I'm curious. I wouldn't be surprised if this times out, but I'm curious. And because I don't know if 1,000 is just like a magic number. 1,000 may not be the worst case just because this may not be monotonically increasing, right? So like, for example, yeah, 998 has so many more steps. But I'm still surprised that 21 is good enough. Or like, it doesn't... I'm surprised that it doesn't trigger the worst case. I'm going to give a YOLO submit. Like I said, I wouldn't be surprised if this fails. But that is actually not expected, honestly. And apparently I also did it not that long ago. On Leap Day, even. But, I think I'm just trying to figure out why this works. Honestly. Without memorization, and we shouldn't memorize anyway, and it's not that much of a deal, that big of a deal. But okay, so let's say we want to try to get 1,000. Then we start 1 0, 1 0. We go to 1 1 for it. We have to do it, and then now we can just go 2 1 3 1 all the way to 1,001, right? Or we go to 2 1 and then we go to 2 2 to copy, and then we go to 1,002, which is so. Oh, I see. So I think. Okay, I guess that makes sense because now next one you go to 3, could be 3 1 or 3 2, but then either way you could just copy it, because 3 1 we already do all the way, and then 3 you can't get to 3 2, I don't think, but then 3 3 you get the 1,003, but this is just 1,000 over 3, roughly speaking. I mean, I think you can actually get there, so maybe that's whatever, but in terms of complexity. And of course, if you kind of write it out that way, because I actually, I'm not gonna lie, I did expect in my head that this was going to be 1,000 plus 999 or 999 plus 998 ... and it becomes n squared. And while I think it's fast enough still in that case, it's still a little bit like sloppy, and it just, takes a long time. But now that I kind of actually write it out, it is 1,000 over 1, 1,000 over 2, 1,000 over 3, which is of course n log n, which is maybe a little bit surprising. But of course 1,000 log n is not, it's brazen. You don't have to worry about it, which is kind of how it came out. Like, it's relatively fast for, so I guess, like, it comes to show, because a lot even though in theory current is the number of characters, which is 0 to 1,000 or 1 to 1,000 or whatever, this is going to be also 1 to 1,000, but a lot of these states are not reachable, right? So I think that's kind of the key. And also, as the clipboard gets higher, current increases higher, which makes it n log n, which I didn't expect until I kind of went through it. And in fact, I kind of just did 1,000 on a whim. I honestly thought it would time out. So it's kind of interesting. Yeah. And by that logic, I guess you could... I mean, I did it with dynamic programming, but if that's the case... I mean, it's only 1,000 square anyway, the number of loops. So you can actually do this with breadth first search as well. So this is kind of like a lazy... like a poor version of breadth first search, I suppose. I guess I'm trying to think. Do you ever go to the same state? Like, is it possible to reach the same state twice? I guess that's what I'm trying to think. No, it certainly is. Like, if you could go to 4 4 or something by going to 4 1 and then 4 4 or you could go 2 1 2 2 4 2 4 4. So you definitely go to the same state multiple times. That's really I mean, I don't know. Honestly, it is a little bit surprising for me, but you know, but still. How did I do it last time? Did I do a breadth first search last time, or just? I did do a breadth first search last time. It turns out. Yeah. So I mean, same idea. But yeah, now I'm just gonna finish the memorization. As I always say, you know, we set this up. So yeah, let's just set it up. So I always set up this way, just so that it's a little bit clear. This is gonna be n plus 1. Right, so I always generally write it this way because I feel like it's easier to visualize the space and stuff like this. And then of course, in this case, we just have if has cache, current clipboard. Yeah. And apparently, yeah, the buffer search is pretty fast. Hopefully with the memorization, it'll be fast too with this one. But yeah, that's all I have for this one, really. But yeah, it's slower. Yeah, I don't know what to say. I mean, it's also possibly slower because we have to initialize all the space, a lot of it unused. For example, like 4-3 is impossible, I think, maybe. So yeah, I don't know. Alright, well, I mean, looks like there are multiple ways to do it. Not too bad. You don't even need to memorize, apparently. But yeah, that's all I have for today, though. Definitely, if you're curious about the breadth first search video, that's only, you know, half a year ago, not even that long ago. I probably did an okay job of explaining it, so try that video as well if you want to get another perspective and to learn it or upsolve another way. But yeah, that's all I have for this one. That's all I have for now. Thanks. Oh, yeah, let me go over the complexity. I guess I never went over because as I said, this is O of n and this is O of n. I want to say that this is n squared, but maybe it's not. Because of what we said, right? Because this thing converges so quickly from all the possible states that maybe it's because I'm trying to think whether current always have to be a multiple of clipboard. Right, because that's the big thing. Because it's easy to say that this is n squared because they're n squared states, but I'm trying to think whether it is always forced that clipboard, or sorry, current is a multiple of clipboard. Because I think clipboard has to be or sorry, the other way around. Current has to be a multiple of clipboard, and as a result, if you kind of do it backwards, then this is just the CIF, and that's why this is actually n log n, with or without the caching. So yeah, this is gonna be n log n. Why is n log n so slow? Am I lying about n log n? I am actually like very curious, honestly. What am I writing? I mean, this does not disprove to n log n. That's roughly like, you know, it's definitely not n squared. Right. But it still feels a little bit slow for n log n. I don't know. Why is this a little bit faster? And why is this so much faster? Maybe it's just because I don't I don't know. And I definitely use a lot more memory from just these things. So definitely a lot of this running time, the second time, is from allocating the memory because we don't even use most of these. So now we have n square space from the memorization where we only do n log n stuff. So this actually dominates. So this is actually a bad memorization if you prove that this is n log n. It's kind of fun to play around with. Alright, well, okay, without the memorization, it does look much more expensive. Is it still n log n? No. Maybe? I don't know. Am I lying about I mean, I guess I could assert this, actually. Oh, well, other than with 0. So, okay, so that's true. So, yeah, I mean, there are some branchiness about it, but the total number of states is n log n, and we have all of one things. I mean, we can actually bring back the memorization, just not in that way, because you can see that we actually save a lot of operations, but I was just lazy about the thing. So you would maybe just, I don't know, let's just write it as like a hash table. So then now if cache, or if current clipboard in cache, then we return cache of current clipboard. I'm a little bit lazy today. I'm just exploring, right? And now, yeah, you can see that it is much, maybe give it a quick submit. Yeah, so here, so you can see how much, it gets hidden away if you have n square, just like initialing the space, right? You see that, like, this is a drastic 140 megs, and also like a lot of 2/3 of the time is on the allocation. So this is where, if you're not careful about memorization, it can definitely get you into trouble. And because of this thing, I removed the search statement, but because of the search statement, it should be only n log n states, and if you memorize, then all these is all 1, so then this becomes n log n. I'm still surprised that this is faster though, by that much, honestly. I mean, I think it makes sense. I see. The reason why this is so much faster is because it has early termination. Because as soon as any point reaches n, we return the distance, which allows us to shortcut throwing out the entire graph. Where here, we actually do throw out the entire graph. We do not branch. You do not do like a branch and bound thing. Because you throw out every n log n possible states, where the other one, the total number of possible states is n log n, but a lot of them are not even reachable because, well, not that they're not reachable, they're just not the shortest way forward, right? For example, if you have 1,000, the shortest move is 21 or something. 21, right? So that means that you have only 21 iteration of these loops before it breaks, and so like it's a summation of that, right? I mean, it's more than 21 while loop, but it's like 21 depth, right? So it's not, and each depth is at most 2 away from the beginning. So that means that this is at most like 40 loops or something like this, right? Or maybe like 60 or something. I can't do math, right? So that's why this is so much faster. It's because of the early termination. If you really want to, so this is memorization, right? With dynamic programming. If you really want to kind of simulate this, and we get rid of it, we can actually do something. We could write branch and bound instead, right? So maybe it will be very similar, but we would have like a distance metric, and then here we have 0. Yeah, and you would like do a branch and bound if current is we return. What do we return? I guess we return D. And then here you just do D plus 1 instead of having it here. D plus 1 instead of having it here, right? And then I think this should work already, but I mean, this isn't what I want yet because it doesn't do the bounding, but yeah, you can see it still visits all the states. It's fine. This is just raw breadth first search, or sorry, depth first search. But as a result, you can do something like I actually don't quite know how to do it. But I would say that it definitely, in this way though, actually the order probably matters. No, I mean, still not yet because we're not branching, right? So, I guess actually the other way makes more sense. But yeah, and then now what you ideally want to do is have some heuristic in which, you know, like I don't know, like maybe if you do like if D plus log n or something like this, log current, like I'm not gonna write it out just because I don't know, I'm too lazy to, but you do some heuristic, like a pessimistic heuristic that gives you an upper bound on the thing, and it's still basically the idea here is that, and I think log current, or not log current, but like log delta or something like this, is already greater than our best result, where best is not this. We don't even need to return, in theory. We would just have like a global thing where best is equal to 0. Here we don't even return. Here we just return. But here we also just return, but we said best is equal to D. Non-local best is equal to min, best is equal to D. So actually this should be infinity still. Right, and then now yeah, so this would be like a structure for so actually let's just remove this for now, and then you can see that this works. So now this is going to be the recursive part, and you can see that this is much faster. But then now you could even make it more faster by making branching, chopping off impossible states, which is something like I said, if D plus, I don't know what the pessimistic bound is. But you could say, like, I mean, a very lazy one is with best is equal to D return, right? We don't even, but in theory, you would do something like a pessimistic thing as well. And you can see that this should, okay, that didn't do anything. Maybe because of the order operation that we did it. But, I don't know. There's just a lot of things to play around with. But I think it all stems from, though, knowing that this is actually n log n number of states, which I didn't expect, honestly. Anyway, that's all I have for this one. Let me know what you think. Thanks for watching. I don't know I wonder if the old Larry, the younger Larry rather, analyzed this and thought it was n log n. Maybe. I don't know. Young Larry is crazy. That's all I have for this one though. Let me know what you think. Thanks for watching. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye bye.